Hello everyone, welcome to ChemE-Shiksha. Today we'll be talking about one of the most important topic of this heat exchanger lecture series, that is heat exchanger design. So if you are targeting any design company, then this topic is very much important for you. So without any further delay, let's talk about this thing. So first of all, when we want to design a heat exchanger, we first need to know what is the heat duty of the heat exchanger. So we know the heat exchange from the cold fluid, that is QC, will be exactly equals to the heat exchange to the or by the hot fluid. That means the amount of heat that will be exchanged by the hot fluid, that will be gained by the cold fluid. So QC equals to QH, and we can write it that M, we know that Q equals to mCp delta T. So from there we can write that MC into CPC into TCO minus TCI is exactly equals to the MH into CPH into THI minus THO. So MC is the cold fluid flow rate, maybe in kg per second. Similarly, MH is the hot fluid mass flow rate. CPC and CPH, these are the heat capacity of cold fluid and hot fluid. Then TCO and TCI, these are the cold fluid outlet and inlet temperature, and THI and THO are the hot fluid inlet and outlet temperature. So to calculate the heat duty, we must know at least one of the fluid flow rate, mass flow rate, either MC or MH. From the literature, we can find out the CP value of cold fluid or hot fluid, and the hot fluid and cold fluid inlet outlet temperature will also be given. So if we know, let's say, the cold fluid mass flow rate, so from MC into CPC into TCO minus TCI, from this we can calculate the heat duty of the heat exchanger. And to maintain that heat duty, what amount of hot fluid we need to supply, that we can calculate using this equation, and we can find out the hot fluid mass flow rate. Now we have to calculate the LMTD, because we know that Q equals to U into A into LMTD. So we need to calculate the LMTD. So for counter current flow, the LMTD is equals to THI minus TCO minus THO minus TCI divided by ln of THI minus TCO by THO minus TCI. Similarly, this is the co-current flow for LMTD. So we know that LMTD is equals to delta T1 minus delta T2 divided by ln of delta T1 minus delta T2. So for hot fluid, or sorry, for co-current flow, let's say this is the hot fluid inlet and this is the hot fluid outlet temperature, and cold fluid, this is the inlet and this is the outlet. So this is the outlet, this is the inlet for hot fluid, this is the outlet for hot fluid, this is the inlet for cold fluid. So for counter current flow, delta T1 will be THI minus TCO, this value. This is the delta T1 and this is the delta T2. So that is the THO minus TCI. Similarly for co-current flow, so this will be this. This is the inlet for cold fluid. This is the outlet for cold fluid. So delta T1 will be THI minus TCI, and delta T2 will be THO minus TCO. Now after calculating the LMTD, we need to calculate the LMTD correction factor, because the heat exchanger might not be only one cell and tube pass. It might be one cell pass, two or four or six or eight tube pass, one cell pass, and multiple tube pass or multiple cell pass also can be possible. So we need to correct the LMTD. Also there are, we know, the three kinds of flow configuration. It might not be only co-current or counter current, it can be cross flow as well, with counter current or co-current. So that's why we need to incorporate the correction factor, that is the Ft. So Ft, in the equation of Ft we have R and S. So this R is actually delta T hot fluid divided by delta T cold fluid, that is Thi minus Tho divided by Tco minus Tci, and S is the delta T of minimum, that is Tco minus Tci, and divided by delta T maximum, that is the Thi minus Tci. So if we know R and S value and the how many number of passes, that like here it is one cell pass and two tube pass, so for that this is the Ft equation. Now from this chart as well we can calculate the correction factor Ft. So this chart is for one cell pass and two tube pass, two or more tube passes. So it can be there are also charts for multiple cell passes. So this is the S value, these are the R value. So let's say we have some S value, R value of 4 and S value of, let's say, 2. So this is a 0.2 and 4. This, let's say, this is a 0.2 value. So we have to go like this. This is a 0.4. So it will cut here, and the Ft value will be around 0.81 or 82. So we will calculate from there. If we know the Ft value or the correction factor, we can calculate the corrected temperature difference delta Tm, that is LMTD into Ft. This is the corrected temperature difference delta Tm, that is LMTD into Ft. Now as we know that Q equals to U into A into delta Tm, that is the corrected temperature difference. So we know Q, that is the heat duty of the heat exchanger. We also know the corrected temperature difference delta Tm, but two are the unknown, that is one is U, another one is the area A. So that's why if we want to calculate the heat transfer area, we need to assume the overall heat transfer coefficient U. So for assuming this overall heat transfer coefficient, there are standard tables. So from there we can assume the value of U. So like for example, if we have steam as our hot fluid and some heavy or light organics as the cold fluid, then these are the ranges. Like for steam and heavy organics, we have the range 600 to 900 watt per meter square degree centigrade. So if we are dealing with some heat exchanger where the hot fluid is steam, the hot utility steam, and the cold fluid is heavy organic, then we can assume the overall heat transfer coefficient value in between 600 to 900. Now after assuming the U value, we can calculate the provisional heat transfer area A, because we know Q equals to U into A into delta Tm. So we know the heat duty of the heat exchanger, we have assumed the overall heat transfer coefficient, and we also calculate the mean temperature difference delta Tm, that is Ft into LMTD. So from there we can calculate the heat transfer area, which is a provisional heat transfer area. Now if we know the provisional heat transfer area, we know that heat transfer is done on the outer surface of the tubes. So A is exactly equals to the tube outside surface area. So A is equals to pi d naught L, which is the outer surface area of a single tube, into number of tubes, that is NT. So from this equation we can calculate the number of tubes, because we know the tube outside diameter, we know the tube length L, and we also know the provisional heat transfer area A. So from this equation we can calculate the number of tube NT. Now after that, in this 8th step, we have to calculate the tube pitch and the tube bundle diameter. So tube pitch PT equals to 1.25 into D naught. D naught is the tube outside diameter. So tube pitch pt equals to 1.25 into d naught. So from there we can calculate the tube pitch, and for bundle diameter db is equals to d naught into nt by k1 to the power 1 by n1. So db is the bundle diameter, d naught is the tube outside diameter, nt is the number of tubes, and k1 and n1, these are the two constant value which depends on the tube pitch and the number of tube passes. So this is the table where for triangular and square tube pitch, the constant value k1 and n1, these are given for 1, 2, 4, 6 and 8 number of tube passes. So when nt, this is a small nt, that is the number of tube passes. So when this is 1, 2, 4, 6, 8, and if the tube pitch is triangular and square, what will be the value of this constant k1 and n1, we can find out from this table, and from there we can find out the tube bundle diameter db using this equation, that db equals to d naught into nt by k1 to the power 1 by n1. Now if we can calculate the bundle diameter db, then from this chart we can calculate the bundle diameter clearance or BDC. So bundle diameter clearance, so you can see here that in this chart, in the x-axis we have the bundle diameter in meter, and the vertical axis we have the bundle diameter clearance, that is the cell inside diameter minus bundle diameter in millimeter. So depending on the type of the cell and tube heat exchanger, whether it is fixed or U-tube, or it is outside packed head, or it is split ring floating head, or it is pull through floating head. So depending on this type of the head or the cell and tube heat exchanger and the bundle diameter, we can calculate from this chart the bundle diameter clearance or BDC, that is the cell inside diameter minus bundle diameter. So if we can calculate the bundle diameter and bundle diameter clearance, so we can calculate the cell inside diameter, because we know that bundle diameter clearance is equals to cell inside diameter minus bundle diameter. So cell inside diameter ds is equals to bundle diameter plus bundle diameter clearance. So using this equation you can calculate the cell inside diameter. Now to calculate the baffle spacing, we know that generally 40% of this cell inside diameter is taken as baffle spacing. So baffle spacing BS is equals to 0.4 into DS, that is the cell inside diameter. Now in the next step we have to calculate the area for cross flow, that is AS is equals to PT tube pitch PT minus D naught, the cell tube outside diameter, into DS, that is the cell inside diameter, into BS baffle spacing, divided by PT tube pitch. So as we calculate the cross flow area or the area for cross flow, then we have to calculate the cell side fluid mass flow rate, that is GS, that will be equals to cell side fluid flow rate in kg per second mass flow rate divided by AS, that is the cross flow area. So then we can so the mass flow rate by the cross flow area, that will be the cell side fluid mass velocity. So after calculating this cell side fluid mass velocity, we can calculate the cell side fluid Reynolds number and Prandtl number. Before calculating the cell side fluid Reynolds and Prandtl number, we have to calculate the cell equivalent diameter. So for square pitch, the cell equivalent diameter DE is equals to 4 into PT square minus pi D naught square by 4 divided by pi D naught by 2, that is equals to 1.27 by D naught into PT square minus 0.785 D naught square. And for triangular pitch DE, the equivalent diameters cell diameter, that is equals to 4 into pt by 2 into 0.87 into pt minus 0.5 into pi d naught square by 4 divided by pi d naught by 2. So we need to calculate the cell equivalent diameter to find out the heat transfer coefficient, because in heat transfer coefficient formula we have the Reynolds number. So for Reynolds number we need to know the cell equivalent diameter, because the cell side fluid is not flowing throughout the cell. There are tubes as well, so we need to deduct that diameter. So that's why we need to calculate the cell equivalent diameter where the cell side fluid is actually flowing. That is the DE, cell equivalent diameter. Now after calculating the cell equivalent diameter, we can calculate the cell side fluid Reynolds number and cell side fluid Prandtl number, because we know that Reynolds number equals to Gs into dE by mu s. Gs is the cell side fluid mass velocity, that is we can also write rho into Vs, rho s into Vs, into the cell side equivalent diameter, that is dE, divided by the mu s, and the cell side fluid Prandtl number will be Prs equals to mu s into Cps divided by Ks, thermal conductivity. Mu s is the viscosity. Now in the next step, step number 17, we have to calculate the cell side fluid heat transfer coefficient. So we know from the equation, that is Nusselt number, cell side fluid Nusselt number NuS is equals to Hs into dE by Kf. So H is the cell side fluid heat transfer coefficient into the cell side equivalent diameter dE divided by Kf, the cell side fluid thermal conductivity, equals to Jh into Reynolds number of the cell side fluid into Prandtl number of the cell side fluid to the power 1/3 into mu by mu w to the power 0.14. So this is the equation for cell side fluid heat transfer coefficient, that Nusselt number NuS is equals to Jh into Res into Prs to the power 1/3 into mu by mu w to the power 0.14. So we have calculated the Reynolds number and Prandtl number for cell side fluid. So we can put over here. Then Jh we can find out from this equation the heat transfer factor Jh. So if we know the Reynolds number and the baffle cut and percentage, baffle cut percentage, whether it is 15%, 25%, 35%, 45%. So it is given over here that if we know the Reynolds number and the baffle cut, we can calculate the heat transfer factor or the Jh. So if we know Jh, we already know the Reynolds number, Prandtl number, we know the mu and mu w. Then we can calculate the Nusselt number, and we also know the dE, cell equivalent diameter, and the cell side fluid thermal conductivity. So then from this equation we can calculate Hs, that is the cell side fluid heat transfer coefficient. So if we can calculate the cell side heat transfer coefficient, after that we have to calculate the cell side pressure drop. The equation is delta Ps equals to 8 into Jf into ds by dE into L by Bs into rho Vs square by 2 into mu by mu w to the power minus 0.14. So the cell side pressure drop delta Ps is depending on this Jf, which is the frictional factor. So from this curve, from this chart, we can calculate the friction factor Jf. If we know the Reynolds number and the baffle cut percentage, we can calculate the friction factor from this graph. Then ds is the cell diameter, de is the cell equivalent diameter, L is the tube length, Bs is the baffle spacing, rho is the cell side fluid density, Vs is the cell side fluid velocity into by 2 into mu by mu w to the power minus 0.14. So from this we can calculate the cell side pressure drop. Now after that we have to calculate the number of tube per passes, that is NTPP. This will be equals to number of tube divided by number of passes. So if we divide the number of tube by number of passes, we can calculate number of tube per passes. So after that, in step number 20, we have to calculate the tube side fluid mass velocity, that is GT. So GT equals to tube side fluid flow rate in kg per second divided by pi di square by 4 into NTPP. So di is the tube inside diameter. So di pi di square by 4, that is the tube inside surface area, a cross sectional area, into the number of tube per passes. If we divide it with the tube side fluid flow rate in kg per second, we will be getting the mass velocity of the tube side fluid. So if we divide this mass velocity of this tube side fluid by rho, that is the density of this tube side fluid, then we will get the Vt, that is the tube side fluid velocity. So Vt equals to Gt by rho t. Now after that we will calculate the Reynolds number and Prandtl number for tube side. So Ret and Prt, that will be equals to Ret equals to rho t into di into Vt by mu t, and Prt equals to mu t into Cpt by Kt. So similarly, then we have to calculate the tube side heat transfer coefficient and the tube side pressure drop using this equation. So for tube side heat transfer coefficient, the equation is the Nusselt number for tube side, that is Hi into di by Kf, is equals to the heat transfer factor Jh into Reynolds number into Prandtl number to the power 1/3, that is 0.33, into mu by mu w to the power 0.14. So again, this Jh, the heat transfer factor, can be calculated from this equation, from this chart. So if we know the Reynolds number and if we know the L by D ratio, then we can calculate the heat transfer factor. So L is the tube length and D is the diameter. So if we know the L by D ratio and the Reynolds number, we can calculate the heat transfer factor JH. So if we know JH, we have already calculated Reynolds number and Prandtl number. We know the viscosity. We also know the tube inside diameter and the thermal conductivity of the tube side fluid. Then we can calculate the tube side heat transfer coefficient. Similarly, tube side pressure drop delta Pt is equals to Np, the number of passes, into 8 Jf L by di mu by mu w to the power minus m plus 2.5 into rho by Vt square by 2. So this m value is 0.25 for laminar flow, and for turbulent flow the m value is 0.14. So Np is the number of passes and Jf is the friction factor, which can be calculated from this chart if we know the Reynolds number and the L by D ratio. Not the ratio, if we know only the Reynolds number, from this curve we can calculate the friction factor Jf. Now after calculating the heat transfer coefficient for cell side fluid and tube side fluid, we can calculate the heat transfer coefficient, overall heat transfer coefficient of the heat exchanger, which is the last step of this heat exchanger design. So the overall heat transfer coefficient is U naught. So the equation is 1 by U naught equals to 1 by H naught plus 1 by H OD plus D naught ln D naught by Di by 2 kW plus D naught by Di into 1 by Hi plus 1 by HID. So H naught is the outside heat transfer coefficient, HOD is the for fouling, the dirt heat transfer coefficient, outside fouling heat transfer coefficient. Kw is the wall thermal conductivity. Do and Di, these are the inside and outside tube diameter. Similarly, Hi, we have the inside heat transfer coefficient, and HID is the inside dirt coefficient. So from this equation we can calculate the overall heat transfer coefficient based on calculating the tube side and cell side heat transfer coefficient. So now if this calculated U value is greater than the assumed U value, so if you remember, we have assumed the U value in the step number 5. So if this calculated U value is greater than the assumed U value, then our assumption is valid and we can go for the design. Otherwise we have to return back to the step number 5. That means if the assumption U value is actually more, assumed U value is more than the calculated U value, then we have to go back to the step number 5 and we have to do the iteration with the calculated U value until the difference of the calculated U value between two consecutive iteration is small. There are also two more things, that is we have to also check the tube side and cell side fluid velocity and the pressure drop of the tube side and cell side, because there is a limit that the cell side velocity, fluid velocity should be within 1 meter per second and pressure drop should be within zero 0.5 bar, and for tube side this pressure drop should be within 1 bar and velocity will be within the 1 to 3 meter per second. So we have to also check this velocity and pressure drop for cell side and tube side, whether they are within the range or not. So this is all about the heat exchanger design. So you have to first start with the calculating the heat duty of the heat exchanger. Then we know that Q equals to U into A into the temperature difference. So the mean temperature difference delta Tm is equals to LMTD into the correction factor Ft. We have to incorporate this correction factor because of the flow configuration and the passes. So delta Tm is equals to Ft into LMTD, and U we have assumed from the standard table. We also calculate the Q, so we can find out the A value of the provisional heat transfer area. So if we know the provisional heat transfer area, from there we can calculate the number of tubes, and from there we are one by one calculating the baffles, the tube pitch, tube bundle diameter, then the cell inside diameter, the baffle spacing, because we want to calculate the cell side Reynolds and Prandtl number, because actually we have to calculate the cell side overall cell side heat transfer coefficient and tube side heat transfer coefficient. So for calculating the cell overall heat transfer coefficient, we have to calculate the cell side and tube side heat transfer coefficient, and for that we have used the Nusselt number equation. And in the Nusselt number equation we have the Reynolds number and Prandtl number, so that's why you have to calculate the Reynolds number and Prandtl number for cell side and tube side. And we have also calculated the cell side and tube side pressure drop, because the pressure drop should be within the limit, otherwise there might be some explosion or kind of things. So that's why we have to calculate the cell side and tube side pressure drop, and it should be within the limit. So these are the references, and thanks for watching this video. If you like this video, please hit the like button, share this video with your all friends, and be a part of a growing network of future ready chemical engineers. Subscribe this channel. Thank you again for watching this video.